Hey there, and welcome. Have you ever just stopped and looked around at your desk, the water you're drinking, even the air you're breathing, and just wondered, what is all this stuff actually made of? Well, today we are diving deep, and I mean really deep, into the secret science of matter to find out. Let's get into it. Okay, so let's start with something simple, like this pot of boiling water. Looks pretty ordinary, right? But on a level you can't see, something amazing is happening. It's like a war is being fought between billions of tiny invisible particles. You've got heat energy trying to tear them apart, and this powerful force of attraction trying to hold them together. And believe it or not, this invisible battle, well, it explains almost everything. So, what do scientists call all this stuff? They call it matter. And the definition is actually super simple. If it takes up space and it has mass, it's matter. The chair you're in, the planet we're on, the most distant star in the galaxy, yep, it's all matter. But that just leads to the next question, doesn't it? What is matter itself made of? To answer that, we have to zoom in. No, I mean way, way in. We're about to shrink down and enter the secret world of particles, the tiny building blocks that basically write the rules for everything we see and touch. But that's a fair question, right? If these particles, which we call molecules, are so mind-bogglingly small that we can't see them, how do we even know they're there? Well, turns out the proof is all around us, in things you can see and do every single day. So check this out. You stir sugar into water. The sugar just disappears, right? But look closely. The water level doesn't really go up. So where did the sugar go? Well, those tiny sugar molecules are now just hanging out in the empty spaces that were already there between the water molecules. This simple trick proves that matter isn't solid all the way through. It's actually full of tiny gaps. And there's more. Ever wonder how the smell of someone's perfume can travel all the way across a room, or how just a single tiny crystal of something can color a huge amount of water? It's because those particles are not just sitting still. Nope. They are constantly moving, bumping, and spreading out all on their own. This whole idea is so fundamental, it has its own name, the kinetic theory of matter. You can think of it as the master rulebook for this invisible world. And it's pretty straightforward. Everything is made of particles, those particles are always moving, and if you add energy, like heat, they just move faster. That's it. So let's break it down to 4 basic rules that all molecules live by. 1. They are ridiculously small. 2. There are always spaces between them. 3. They never, ever stop moving. And 4. They're always pulling on each other, kind of like tiny magnets. These 4 simple rules are the foundation for, well, everything. Okay, now that we know the rules of this molecular game, let's use them to understand something we see all the time: solids, liquids, and gases. They aren't actually different types of stuff. It's all the same stuff, just with its particles behaving in very different ways. Let's see how this works. Over on the left, we've got a solid. See how the particles are packed in super tight in a nice, neat pattern? The attraction between them is so strong they can really only vibrate in place. But now, look at the liquid on the right. Give those particles a little more energy and they can break free and start sliding and gliding past one another. Now let's crank up the energy even more. In a gas, the molecules are moving so incredibly fast that the forces of attraction just can't hold on anymore. They are flying all over the place, bouncing around and filling up whatever space they can find. And the gaps between them are absolutely huge compared to a solid or a liquid. This table here is a perfect summary. A solid keeps its shape and volume because its particles are locked down by strong forces. A liquid flows to take the shape of its container, but its volume stays the same because the particles are still sticking together. And a gas, no definite shape, no definite volume, its particles are just free agents. It all goes back to that big battle between movement and attraction. So if energy is the big difference maker here, what happens when we start adding it or taking it away? This is where things get really cool, because this is where matter starts to transform, changing from one state to another right before our eyes. And this diagram shows that constant cycle. You add heat to a solid, it melts into a liquid. Add more heat to the liquid, it vaporizes into a gas. Then you can go backwards. Take heat away and a gas condenses into a liquid, which can then freeze right back into a solid. It's this beautiful, constant dance, and it's all powered by energy. But here's a little mystery. Look at this experiment. We're melting wax, right? We're heating it up, the temperature climbs to 55 degrees Celsius, and then it just stops. It stays flat for several minutes, even though we're still pumping heat into it. So what's going on? Where is all that energy going? The answer is a really cool concept called latent heat, which literally means hidden heat. See, during a change of state, the energy isn't being used to make the particles move faster. It has a much bigger job to do. It's being used to win the war against those forces of attraction. All that heat is being spent breaking the bonds holding the particles in place. Only after the bonds are broken can the temperature start to rise again. And those special temperatures where all this action happens, we call them the melting point and the boiling point. For water, we know these really well, right? Ice melts into water at 0 degrees Celsius, and water boils into steam at 100 degrees Celsius. Every pure substance has its own unique set of these numbers. All right, so we've traveled into the heart of the molecular world and learned its rules. Now, let's zoom back out and see how this secret science is playing out all around us in ways that you probably never even realized. Now, you know about boiling, but there's another, sneakier way for a liquid to become a gas: evaporation. The huge difference is that boiling happens at one specific temperature all through the liquid. Evaporation, though, can happen at any temperature, and it only happens right at the surface. That puddle drying up on the sidewalk, it's not boiling, it's evaporating.
And here's the coolest part, literally, evaporation causes cooling. How does it do that? Well, think of it this way. At the surface of a liquid, it's the fastest, most energetic particles that have enough oomph to escape into the air. And when they leave, they take all their heat energy with them, which lowers the average energy, and therefore the temperature, of all the particles they left behind.
And this isn't just some textbook theory. You see it working everywhere. It's why water in a clay pot stays cool. It's the entire reason sweating works to cool our bodies down. It's why a wet cloth on a forehead helps with a fever. And hey, even pouring hot tea into a saucer to cool it down, that just gives more surface area for evaporation to do its cooling magic. It's physics in action. Which brings us to one last big question to leave you with. We've just learned that everything, solids, liquids, and gases, is mostly just empty space between particles. So, if your hand is mostly empty space and the table it's on is mostly empty space, what are you actually feeling when you touch it? Something to think about. Thanks for tuning in.